Hello guys, welcome back to our YouTube channel. I am Ranin Sen. In this lecture we are going to start with transformer, in which first we will discuss about the introductory part of a transformer and then we will move on the principal operations of a transformer. Before we start the lecture, first of all I would like to say that if you guys are new on our YouTube channel and if you still not joined on our YouTube channel, then please click on the subscribe button and also hit the bell icons for upcoming notifications. So let us start with today's topic, that is transformer. This is the overview of a transformer. Transformer is nothing but it is a static device in which we can convert from one level of voltage to another level of voltage. Let me explain how it works. These transformer is just used for step up and step down the voltages. Step up and step down the voltages. These transformer is made up of magnetic material like ferromagnetic material. The best example of ferromagnetic material is iron. Let me assume that the N1 is the number of turns of the primary coil and N2 is the number of turns of the secondary coil. Here, primary of the transformer means where we supply the AC voltage. Supply side of the transformer is called the primary of the transformer, and secondary of the transformer means where we connect the load. The load side of the transformer is called a secondary side of a transformer. Now, when we supply the AC voltage, this is the sinusoidal voltage. This sinusoidal waveform indicates the AC voltage. When we supply the AC voltage like 230 volt RMS voltage to the primary side, for example 230 volt RMS to the primary side, and with respect to this, when we get the secondary side voltage is less than the primary side voltage like 110 volt RMS, that means this kind of transformer is called a step down transformer. And when we will get secondary side voltage more than primary side voltage like 350 volt RMS, that means this kind of transformer is called a step up transformer. Means when V1 is greater than V2, it means that a step down the voltage, or we can say step down transformer, and when V1 is less than V2, it means that a step up the voltage, or we can say that a step up transformer. As you can see that the variations of the coils of the secondary side means N2. When we change the number of turns of the secondary coil, it means we will change the voltage level of secondary side. The secondary side voltage is totally depends on the number of coils of the secondary side. When secondary side when number of turns of the coils of the secondary side increase, then its voltage level is also increased. When number of turns of the secondary coil is decreased, then their secondary side voltage level is also decreased. Okay, now come to the point. This transformer is called a pole mounted transformer. This transformer is called a pole mounted transformer. pole mounted transformer are electric utility distribution transformer that are mounted on an electric pole like wood or concrete. Like wood, concrete, or etc. Pole mounted transformers are the common breadbox transformers used for converting distribution voltage to the 120 by 240 voltage power, which is basically used by consumer or used by homes. Now, what is the definitions of a transformer? A transformer is a static device which consists of two or more stationary electric circuits interlinked by a common magnetic circuit for the purpose of transferring electric energy between them. The transfer of electric from one circuit to another takes place without a change in frequency. Let us visualize what is the meaning of magnetic circuit, and we will try to understand the difference between the electric circuit and magnetic circuit. Let us see. Now this is the electric circuit, and this figure is called a magnetic circuit. When we closed the switch, this is the switch. When we close the switch, the electric circuit follow the closed path. After closing the switch, the electric circuit follow the closed path. A closed path is a path in which electrons from a voltage or current source. The point where these electrons enter an electric circuit is called the source of electrons. Now come to the magnetic circuit. A magnetic circuit, in between the two electric circuit, this is the primary side of the transformer, is electric circuit 1, and secondary side of the transformer is another electric circuit, which is electric circuit 2. In between these two electric circuits, there is a magnetic circuit. Magnetic circuit is made up of magnetic materials like ferromagnetic materials like iron. When we supply the voltage to the coil of a magnetic circuit, then magnetic circuit energized, and when magnetic circuit energized, then it will create a flux, and that magnetic flux will travel throughout the magnetic circuit of a magnetic material. Okay, this is the basic difference between the magnetic circuit and electric circuit. Now guys, these all about the basic introduction part of a transformer. Okay, let us move on the principal operation of a transformer. Before this, first we will discuss about the Faraday's law of electromagnetic inductions. Why we study Faraday's law of electromagnetic inductions? Because Faraday's law of electromagnetic inductions explain the working principle of a transformer, motors, generators, and inductor also. Okay. So the law is named after Michael Faraday, who performed an experiment with a magnet and coil. Let's have a look what he did in this experiment. See, this is the Faraday's first law of electromagnetic inductions. It states that any change in the magnetic field of a coil of wire will cause an EMF to be induced in the coil. These EMF induced is called induced EMF, and if the conductor circuit is closed, the current will also circulate through the circuit, and this current is called induced current. Okay, now in this experiment, Faraday takes a magnet and a coil and connects a galvanometer across the coil, Now at starting, when magnet is at rest positions, so the needle of the galvanometer, so there is no deflections in the galvanometer, so the needle of the galvanometer is at 0 positions. Okay, now what happened when the magnet moved towards the coil like this? When magnet moved towards the coil, the needle of the galvanometer deflects in one direction like this, In the similar manner, when the magnet moved away from the coil, in this case the needle of the galvanometer move in another direction, means opposite directions. So what he observed in this experiment, it is seen that the faster the change in the magnetic field, the greater will be the induced EMF or voltage in the coil, means whatever the voltage is induced in the coil, that totally depends on the rate of change of magnetic field. If the faster the change in the magnetic field is performed, the greater will be the induced EMF of voltage in the coil. That's all about the Faraday's first law of electromagnetic inductions. This is also called the dynamic induced EMF. Dynamic induced EMF. Now in next law, that is called the Faraday's second law of electromagnetic inductions. In Faraday's second law of electromagnetic induction, it states that the magnitude of EMF induced in the coil is equal to the rate of change of flux that linkages with the coil. The flux linkage of the coil is the product of the number of turns in the coil and flux associated with the coil. See, this red curve is the magnetic line of force. This magnetic lines of force, or we can say these fluxes continuously change with respect to time. Whatever the rate of change of magnetic flux is developed by the AC source. AC source means AC source is also in sinusoidal natures, because we know that the magnitude of the AC voltage is continuously changed with respect to time. So due to this AC source, we have the flux. That flux is the rate of change of flux. In short, whatever the induced EMF in the coil A, that EMF induced is the rate of change of flux with respect to time in that coil. In mathematically, induced EMF is N1 d phi by dt. Let us assume that the N1 is the number of turns of the coil A and N2 is the number of turns of the coil B. So whatever the rate of change of flux with respect to time is linked in the coil A of turns N1, in that coil we have induced EMF, that is E equals to N1 d phi by dt. Okay, now when we connect the circuit in coil A and we also connect the lamp, so the circuit is followed the closed path. When coil A followed the closed path, that means the lamp A will work, because in coil A the flux is continuously change with respect to time. But in coil B, sometimes the flux is linkage in the coil B, but sometimes in the flux is not linkage in the coil B. When the flux is linkage in the coil B, at that time the lamp B will turn on, otherwise lamp B will not turn on, otherwise the lamp B turn off. At what time the lamp B is turn off? When magnetic lines of force does not link in the coil B, at that time lamp B will not work. When magnetic lines of force, or we can say the rate of change of flux with respect to time, is linked in the coil B, at that time the lamp B will turn on. Okay, actually the EMF induced in the coil is minus N1 d phi by dt. Why minus sign? Because according to Lenz's law, the directions of the induced current will be such that the magnetic field created by the induced current opposes the initial changing magnetic field. In short, according to Lenz's law, flux always opposes. Due to oppositions, minus sign, that's why minus sign is included in the induced EMF, in the equation of the induced EMF. Okay, so these all about the Faraday's law of electromagnetic inductions. These law and working of transformer is totally based on the, or we can say whatever the AC machine is present in this universe, that all the machines is based on the Faraday's law of electromagnetic inductions. Okay.